Hi guys, welcome to another one of my lectures, and today I'll just be doing a brief introduction to both a CSEC as well as the NCSC topic and a CAPE topic. I'm laying the foundation, and it is called magnetism. Now, magnetism is tied in normally with electricity because it is an effect of an electric current, where anytime you have an electric current you have a magnetic field. Now when you think of the concept of magnetism, you always think about a magnet. Now there are magnetic materials which can exist naturally, right? Like lodestone, etc., and they exhibit magnetic properties. So a magnet, or any kind of magnetic material, is considered magnetic if it exudes or it allows a magnetic force to be experienced. So when I talk about, guys, a magnetic force, I'm talking about either an attractive force or I am talking about a repulsive force. So when either of these forces are exerting on another object, right, similarly of the same magnetic material, then you say that magnetism is in effect. Now, when we look at the structure of magnetic materials, right, and let's look at an example of iron. Right, iron is a very popular magnetic material, and it is often described as a magnetically soft material. Now, many times within iron, you will find here that you have what we call tiny domains, which encompass or make up all different magnetic materials. Now, these domains are themselves tiny little magnets. So here you would have the arrowhead representing a north pole, and you would have the end of the arrow representing a south pole. So normally you would have the magnetic material consisting of a series of domains which are haphazardly arranged or arranged in an orderly fashion. If the domains, which are themselves tiny little magnets, are arranged in this random nature, then the material is described as unmagnetized, where it has a magnetic effect, but that magnetic effect is not experienced because of the arrangement of these domains. So if I wanted this piece of iron to function as a magnet, then I would need to magnetize the material. How do I do that? By aligning the domains. Now, there are two ways I can align the domains. The first way is a more permanent way, which is called stroking, and the second way is a temporary way, which is called induction. Now, let's go back to the unmagnetized material. So here I have this unmagnetized material, and if you take a known magnet, right, your north pole, and you drag it along the surface of this unmagnetized material, and you do it in a circular fashion, then the north pole of this magnet is going to force the south poles of the domains to align. So the green arrows represent what would happen, and the effect is permanent because it's physically rearranging the alignment of the domains. So now what you will end up with is all of the south poles of the tiny domains facing one direction and all of the north poles facing the other direction. Now, if you have induction, we're taking now a magnet. So again, you need a magnet to forcibly align these domains and so induce magnetism. So I take this magnet and I'm going to place, right? I am going to place an unmagnetized material near to it. Remember, guys, your unmagnetized material has this random haphazard arrangement of domains. So what happens is that the north pole is going to pull the south pole of the domains Because remember, your north pole and south pole of your known magnet, right? Remember, this is your known bar magnet here, will have magnetic fields, right? And we look at that just now. And it is the fields that exert a force that force these tiny domains to become aligned. So in the same way here, you have the south poles will pull the north poles of the domains. So the effect of it is this. You're going to have your magnet here, and then you're going to have attraction now, right? And if I have another piece of unmagnetized material placed adjacent, it will follow suit, where the south poles become aligned. So you have the south poles and you have a north pole, and you have the south poles and then you have a north pole. Because as you know, the general rule of thumb is opposites attract. So here, you're going to have the tiny north poles of the domains, and then it's attracted to the south pole in the bar magnet. Again, if I attach another material like this, I am seeing this effect here. Now, if it is, I were to remove totally these two, then my entire line or chain of adjacent materials will no longer be magnetized, and their domains will return to that haphazard arrangement. Now, when we talk about a magnetic field, I mentioned before that we were talking about a bar magnet. And a definition of magnetic field is that it is a region around a magnet, and I'm going to extend it to also a current carrying conductor, which is basically a fancy way for saying a wire with a current, right? Where you have a force field. Right? You have a force field existing. Now here, right, if you look at a typical bar magnet, right, we have to, according to your syllabi, all of them, CAPE, CSEC, and NCSE, understand the directions of the field lines. So here, you have the field lines extending out of the north and the field lines extending into the south pole. Now, the field lines go from north to south, so you have a pattern existing like this. Now, field lines, because they represent a force, are considered as a vector quantity. So here, the field lines go out of the north and they go into the south. So you're probably saying, okay, so how is it that that direction had come to be? Well, we define it as the direction of magnetic field lines are the direction in which a free north pole would move if placed at a point in the field. Right? So here, if you have a north pole, it would have been pushed away from a north pole, hence the field lines directed out. If you place another free north pole here, it would have become attracted to the south, so hence the field lines go in. And the last thing I want to touch on in this introductory video are the field line patterns between two adjacent north poles, and if you had two opposite poles. So here, your field lines typically point away from the north, and they point north to south. They go into the south. Here, the fields go north to south, and then here they go into the south here. So they go north to south, they go into the south here. Now, because these field lines kind of push against each other, there is a region, and I'm going to call that region X, where the field lines don't pass. And because your field lines don't pass, you would have a region where there is a lack of field lines, or you would have no repulsive force. You would have, a repulsive force. Let's say no. You would have a repulsive force existing. Right? And here, if you look at having opposite poles, like if you have a north to south here, and you have a south and a north here, the field lines go out of the north into the south. And when field lines tend to follow each other, that is how you end up having a force of attraction. So it goes out of the north, right? So here you have the field lines following each other. So it corresponds to an attractive force. So stay tuned, I'll have more videos, follow-up videos on magnetism.